We are in Chapter 11. This is Video 2. Section 11.2 is Contingency Tables. In this section, we use standard statistical methods to analyze frequency counts and contingency tables, which are also called two-way frequency tables. So a contingency table or a two-way frequency table is a table consisting of frequency counts of categorical data corresponding to two different variables. The first test that we have in this section is called the test for independence. And this is when we test the null hypothesis that in a contingency table that the row and the column variables are independent, hence the name. So that is that there's no dependency between the row variable and the column variable. The idea behind testing these types of hypotheses is to compare the actual counts to the counts that we would expect if the null hypothesis was true and the variables are independent. So in a chi-squared independence test, the null and the alternative hypotheses are always going to be H0 and H1 are given here, star those. H0 is going to be that the variables are independent, and then H1 is going to be the variables are not independent, or you can also write this as dependent. So below this, we have some steps to determine the expected counts in a test for independence with a TI-83 or 84 calculator. Notice this is just to determine the expected counts. This isn't actually conducting our test yet. We'll get to that momentarily. Step 1, we're going to go to second, x inverse or x to the negative first power. And you'll notice that right above that it says matrix. Then we're going to go to edit, hit enter on A, and it has brackets around it. And those brackets are telling us that it's a matrix. So it says enter row and columns, don't include the totals, so rows and columns, and enter the data values for the matrix. And if you're unfamiliar with matrices, it's going to be written as rows by columns. And rows are horizontal and columns are vertical. And so you put in a 2 by 3, or in this case, the way I drew it is going to be a 3 by 4. And then you're going to enter in the data values into the matrix. Then you're going to hit second mode. And then step 2, we're going to go to stat, test, and go down to chi-squared test. And this should be on both the 83 and the 84 calculators. So chi-squared test. And observed is going to be matrix A, and your expected should be matrix B. Hit calculate, select enter, and it's going to run the test for you, and it's also going to calculate those expected counts for you in matrix form. And so in order to see your expected count, you need to look at step 3, and you're going to go to second to x inverse, again where matrix is. You're going to select B, hit enter twice, and you should see the expected counts. You might have to scroll left and right to see them all. So we have an example right below. This says a sociologist wants to discover whether the sexual activity of 15 to 19-year-old females and family structure are associated. She randomly selects 380 females between the ages of 15 and 19 years of age and asks them to disclose family structure at age 14 and whether he or she has had sexual intercourse or not. The results are shown in the table below. Compute the expected values. So it just wants our expected values of each cell under the assumption of independence. So again, it says under the assumption of independence. So this is going to be that chi-squared test that we'd be using, the test for independence. And so we are given our observed data. And so we need to first put this data into matrix A. So put data into matrix A. And then we have to go to stat test and then go to chi-squared test. On your graphing calculator, to get the expected counts, we need to first enter in our observed counts. So to do that, we're going to go to second, x inverse, it has x to the little negative first power, And you'll notice matrix either with it like it is on the app, or it might be above the key. And you'll see matrix A, B, C, D, E, F, and so on. And this is where you would designate where you want to put this matrix. And I'm always going to select it to go into matrix A. So I'm going to go over to Edit and then select matrix A. Matrix A is a 2x4 matrix, so 2 rows and 4 columns. If you have a graphing calculator, it writes it as a 2 and then an X, meaning by, and then 4. And we're going to enter in all those cells. There's a total of 8 cells for this problem. Double check your numbers to make sure you entered them correctly. Once you have all those values entered, you're going to get out of the matrix mode. And to do that, you hit second mode, and it says quit with the mode button. And next we need to run our test. So to do this, we're going to go to Stat, scroll right to Test, and then go down to chi-squared test. And our observed matrix is matrix A, our expected matrix is matrix B, and that's where it's sending those values is matrix B. And you'll notice we have a chi-squared and a P value. But what I'm interested in for this problem is matrix B, which is those expected counts. And so in order to see those, I need to go back into my matrix mode. So I'm going to go to second, X inverse, or matrix, and you'll notice that B now has 2 times 4 on your calculator, and that means 2x4 it is also, and that should be where those expected counts are. So select matrix B, and it should put a B with those brackets around it. Select enter, and you should get those values for our expected counts. In order to see all the expected counts, you might need to scroll right or left in order to see them all. We're going to round each of these counts correctly to 3 decimal places. From the graphing calculator, we get matrix B, which again is our expected counts, or expected frequencies. And it's written in the same form as it is given in the observation matrix. I'm going to go ahead and round everything 3 decimal places. So we have 78.553, 52.368, 41.895, and 26.184 for the first row. Second row is going to be 71.447, 47.632, 38.105, and 23.816. And so this is what you would expect to see if the variables are independent. And so you can look at what they observed and what you would expect to hold true if, again, that null is true, which is that the variables are independent. So on the next page, we have the test statistic for a test for independence. Again, it's going to be our chi-squared, and we discussed this in the last section with O representing observed counts and E representing the expected counts. And you would subtract expected and observed and square it, and then divide it by the expected, and then sum them up, and that's going to give you your chi-squared test statistic. This is approximately follows the chi-square test statistic with R-1 times C-1 degrees of freedom. So R is the number of rows and C is the number of columns. In the contingency table, provided that all expected frequencies are greater than or equal to 1 and no more than 20% of the expected frequencies are less than 5. So on the next box, go ahead and start. And this is the chi-square test for independence. So this time we're actually going to conduct our test for independence. And it is with an 83 or 84 graphing calculator, so it should work for everybody. So to test the association between or independence of 2 variables in a contingency table, use the steps below. So step 1 is determining our null and our alternative hypotheses, which again, the row variable and the column variable are independent in the null, whereas they are dependent or not independent in our alternative. Step 2 is alpha. Step 3 is verify the requirements for the test are satisfied, and those are listed here. So again, the data has to have been randomly selected. Sample data consists of frequency counts in a two-way table. For each cell in the contingency table, the expected count is at least 5. And then to get to our test, we're going to go to stat test, and for me it was C, which is the chi-square test. Observed is matrix A, expected is matrix B like we saw earlier, and then calculate, select enter. We are going to get chi-squared, which is our test statistic, and P, which is our p-value, and then also DF, which is our degrees of freedom, which is going to be rows minus 1 and columns minus 1 multiplied together. And then step 5 is going to be if the p-value is less than alpha, then we reject H naught, and then we're going to state our conclusion. So the same example that we looked at and we calculated our expected counts is given. And so part A says verify that the requirements for performing the chi-square test for independence are satisfied. So the only thing that we need to check are given to us up above in step 3. So the first one is that they need to be randomly selected, so it needs to be a simple random sample. And the second thing is that the sample data consists of frequency counts in a two-way table. And so they are. And then the third thing is going to be, so this is data in a two-way table or a contingency table. Nothing's missing. And then for 3, it says for each cell in the contingency table, the expected counts are at least 5. So I'm going to say all cells are greater than or equal to 5. So we're good. We can go ahead and conduct this test. So part B says to compute the chi-squared test statistic. From the calculator, we get chi-squared is equal to 10.357. And again, because we're testing for independence, and we have the chi-squared test, which is what we are using. Part C is on the next page. And part C says to test whether family structure and sexual activity of 15 to 19-year-old females are independent at the alpha equals 0.05 level of significance. So a lot of times students struggle with understanding what test they need to use for these types of problems that are presented in chapter 11. And so since it says independence, right away I know I'm going to be doing that chi-square test for independence. So look for those keywords before you start the problem. Also make sure that whenever you do testing, you need to list your null and your alternative. So again, the null is that those variables are independent and we need to use the correct problem terminology in order to write our null and alternative. And so the two variables that we have are family structure and sexual activity of females between the ages of 15 to 19 are independent, and then again same thing but dependent for age 1. So family structure and sexual activity of 15 to 19-year-olds. So 15 to 19-year-old females are independent. Then I'm going to write the same thing, but it's going to be instead that they are dependent. So of 15 to 19-year-old females are dependent. On your graphing calculator, we're going to go to second matrix or X inverse, and then we're going to go to edit and go to A, select enter, and this time we have a 2x4 matrix. And we need to enter in those values of each cell individually. Select enter after each one. And then second mode, which quits us from that matrix screen. And then we need to run our test. So we're going to go to stat, test, go down to chi-squared test, Again, our observed is in matrix A, expected is in matrix B, and from here we're going to get a chi-squared test statistic, which is what we need. And I'm going to round that 3 decimal places to 10.357, and you'll realize that it is a rather large value, so our corresponding p-value is rather small. And we need the p-value for part C and the test statistic for part B. From the graphing calculator, we get a p-value equal to 0.0158. And we need to compare this to alpha, and alpha was given to us as 0.05. So this is definitely less than alpha, which is equal to 0.05. And since our p-value is so small, and that's less than alpha, that probability of type 1 error, we are going to reject our null. So reject H naught. So I'm going to write a conclusion here. So there is sufficient evidence. So there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that, and again we already wrote down H1, and that is that family structure and sexual activity of 15 to 19-year-old females are dependent. So I'm going to go ahead and copy that down. So to conclude that family structure and sexual activity of 15 to 19-year-old females are dependent. And so since we rejected our H naught, we know that we can say that we have enough evidence to show that family structure and sexual activity of 15 and 19-year-old females are dependent. There's some kind of relationship between the two. We don't know what that relationship is, but there is some kind of association, relationship, correlation between these two. Part D says compare the observed frequencies with the expected frequencies. Which cells contribute the most to the test statistic? Was the expected frequency greater than or less than the observed frequency? What does the information tell you? So if you look back at your observed and your expected counts, you'll notice that in just comparing them, if you look at like the first cell here, the first one you would expect there to be about 78, almost 79 girls that would have answered yes, and both biological or adopted parents they were living with at the time of them being 14, whereas they found 64 in their study, and you can see the difference there. So the biggest difference is going to be when both parents are present. If you look at the numbers there between the observed and the expected at all of the cells, and the biggest difference would be between those values and the observed and the expected. So the biggest difference is between observed and expected when both parents are present. And the reason why this contributes to a larger test statistic is that you subtract your observed and your expected and then square it. So the bigger that difference is, the larger that it's going to cause your test statistic to be. And it says the second question was the expected frequencies greater than or less than the observed frequencies? And so was one in one way and one in the other way? And then what does information tell you? It tells us that they assumed that it was supposed to be independent, however it wasn't, that there is again some kind of dependency between these two variables. So the next test that we have, so chapter 11 has many different tests is going to be the chi-square test for homogeneity and proportions. And this is to test whether the different populations have the same proportion of individuals with the same characteristic. And so it says right here, it says the procedure for performing the test for homogeneity is identical to those for the test for independence. So I did not put the steps in here twice, so make sure you go back and you look at that to refresh your mind. You need to be using the chi-squared test. So we're going to use chi-squared test. And so in the chi-squared test for homogeneity of proportions, the null and the alternative hypotheses are always going to be. So again, something to write down and make sure you know for your exam. So H0, the null is going to be the proportions are all the same. So they're going to all be the same, and again, we're talking proportions. And then our alternative is going to be at least one proportion is different. The next example says, in a recent survey conducted by the Pew Research Center for People and the Press, a random sample of adults 18 years of age and older living in the continental U.S. were asked their reaction to the word capitalism. In addition, the individuals were asked to disclose which political party they most associated with. Results of the survey are given in the table below, so you can see positive and negative reaction to the word capitalism, and then Democrat, Independent, and Republican Party is what they mostly associate with. And so right below that it says, does the evidence suggest a different proportion of individuals within each political affiliation reacts positively to the word capitalism? So for this problem it says a different proportion of individuals within each political affiliation react positively to the word capitalism. And so right away I notice it says the word proportion. And with this, I notice that there's more than one group here with talking about political affiliation. And there's 3 groups. And so we learned about dealing with 2 proportions back in chapter 9, 1 proportion in chapter 8. And so this is almost like an extension of that. And so in order to do the chi-square test for homogeneity of proportions, we have to have a null, which would be that the proportions are all the same. And then H1 is going to be that at least one proportion is different. So for this problem, I'm going to go ahead and say H0. And you can write it out with words. I'm going to write it out with more symbols. I'm going to say proportion of Democrats is equal to the proportion of independents. It's equal to the proportion of Republicans. And saying this is Democrats, Independent, and Republican is what I'm calling those. So this is saying that the proportions are all the same regardless of political affiliation. And again, this is talking about proportions of the people that are reacting positively to, and I'll just say capitalism. Our alternative hypothesis, or H1, is going to start off with at least one proportion. So at least one proportion is different from the others. We need to put these data values into a matrix. And again, we're going to call this matrix A. And matrix A is a 2 rows by 3 columns size. And so we're going to go ahead and put the numbers into matrix A and then use our chi-squared test. On our graphing calculator, we're going to put our data first into our matrix. And to do that, we're going to go second X inverse or matrix. And then we're going to go to Edit on A. And remember, our matrix is a 2 by 3. And then we need to enter in all those values here. From here, we're going to go to second mode, which is going to quit and make it come out of that matrix mode. And then we need to run our test. So to run our test, we are going to hit Stat, scroll right to Test, and we're going to go to chi-squared test. Our observed is going to be matrix A, and our expected is going to be matrix B. and you will see a test statistic there, chi-squared, which is rather large, and then you'll also see a corresponding p-value, which is e to the negative fifth, which means times 10 to the negative fifth. So make sure you round that correct 4 decimal places, and it should be 0.0000. From the graphing calculator, we get a p-value equal to 3.37 times 10 to the negative fifth. And so again, moving the decimal 5 times to the left, this is going to round to 0.0000. And this is definitely less than our alpha value, and alpha was given to us as 0.05. And so this means we are going to reject H naught. So from here we need to write a conclusion, and we're going to go ahead and say there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that at least one proportions, and I'm going to add in a little bit more from what I wrote up above, so at least one proportion of, and I'm going to take the wording that's up here, of individuals within each political affiliation reacts differently to the word capitalism. Macnamar's tests for matched pairs. The method used previously were based on independent data for a 2x2 contingency table consisting of frequency counts that result from matched pairs. The frequency counts within each matched pairs are not independent, and for each case we can use Macnamar's test of the null hypothesis that the frequencies from the different categories occur in the same proportions. So right below that we have a box. And this is testing a hypothesis regarding the differences of two proportions. This is for dependent samples. And again, it's a 2x2 matrix that we're going to have. And there's some formulas here, and you'll notice these F and the sub numbers here. So talking about what those mean, since it's a 2x2 matrix, that means that we have a total of 4 different cells. So the first cell would be F11, and then F12, and then F21 and F22. So those little sub numbers are telling us rows first and then columns. So the first value that we have is row 1, column 1. The one next to that is F12, so row 1, column 2. Likewise on the second row, we have F21, so row 2, column 1, and F22 is row 2, column 2. And so it says the sample must be dependent. This is what you would have to verify. And F12 plus F21 is greater than or equal to 10. Step 1 is to determine your null and alternative hypotheses. So definitely something that we should know for dealing with Macnamar's test for matched pairs. So H naught is going to be the proportion between the two populations are equal. Since we're only dealing with two populations, we can definitely write this as P1 is equal to P2. You can also write it out with words. And then H1 is going to be the proportion between the two populations are different. So again, you can also write this as P1 is not equal to P2. Step 2 is select your level of significance, which again is usually given to us. And then for this test, we don't have a nice button to use on our calculator. We're going to have to do a little bit more of the calculations by hand. So step 3 says compute your test statistic. And our test statistic formula is given here. It's chi-squared is equal to, and it's going to be the absolute value of F12 minus F21. And you take the absolute value of that, which again turns positive since it's talking about a distance. Subtract 1 from that, and then square it, and then divide by the sum of F12 and F21. So first thing we're going to do is calculate chi-squared. Step 4 is going to be to calculate the p-value using chi-squared CDF. So we're going to be using chi-squared CDF. And in order to do this, you need to go to second on your calculator button, and then vars. And for me it was number 8, which is chi-squared CDF. And for chi-squared CDF, you are going to have your lower bound, your upper bound, 1, which is our degrees of freedom, and that's because it's a 2 by 2 matrix, so subtracting 1 from your rows and 1 from your columns and multiplying them together, you would have 1. And because we're dealing with chi-squared, if you remember, it is not symmetric. It depends upon your degrees of freedom, but it always goes off to the right. So our actual upper bound here is going to be 1e99 since it goes on to infinity. And so from this, we're going to get our p-value. And if the p-value is less than alpha, we reject our null hypothesis. And we're going to state our conclusion. And this lower bound here that we're going to put in is going to be our test statistic. And I'll put down chi-squared test statistic. And then don't forget to state your conclusion. So right below this, we have an example. And the example says a Gallup organization survey asked 1,041 adult Americans whether they felt low-income people paid their fair share of taxes. Then they asked whether they felt high-income people paid their fair share of taxes. For each income group, a success is identified as individuals who feel the person pays his or her fair share of taxes. Is there a significant difference in the proportion of adult Americans who feel high-income people paid their fair share of taxes and the proportion who feel low-income people pay their fair share of taxes? Use the alpha equals 0.05 level of significance. And so our two-way table or a contingency table that we have listed here, you'll notice low income and high income, and then fair share and not fair share. And I'm going to go ahead and abbreviate my two groups as HI for high income and LI for low income. So looking at this, it says, is there a significant difference in the proportion of adult Americans who feel that they paid the high-income people paid their fair share of taxes along with low-income people paying their fair share of taxes? So they asked each group first if they thought high-income people paid their fair share of taxes, and then asked and see if they thought low-income people paid their fair share of taxes. So we're dependent data is what we're dealing with, since you're asking that same question twice to the same person. So right away I know that I'm dealing with dependent data, and it's also dealing with proportions, which I know is going to be that Macnamar's test. I also want you to note that it's a 2 by 2 matrix, which is the only way that Macnamar's is going to work. We can say then that we are dealing with dependent data, and it's also asking for proportions, which again means that we're going to be using that Macnamar's test. So in order to do this, we would have to check to make sure that F12 plus F21 is greater than or equal to 10. And I will go ahead and write down, this is F11, this is F12, this is F21, and F22, just so we can keep track of these values. And if you add together F12 and F21, it's clearly greater than or equal to 10. And so we can go ahead and do this. And then we also said that the data is dependent. The samples are dependent. So our null hypothesis, H naught, is going to be that the proportion for high income is going to be the same as the proportion for low income. And likewise, H1 is that they're different. So the proportion of high income is not equal to the proportion of low income. The next thing that we need to calculate is our test statistic, chi-squared, which the formula is given up above, which is the absolute value of F12 minus F21 minus 1, and then squaring that all over the sum of F12 plus F21. So I'm going to go ahead and substitute in these values here. We know that F12 is 146 and F21 is 274. Squaring that, and then sum put in the denominator, so we're going to have 146 plus 274. Subtracting 146 and 274, we do get a negative answer. However, you're going to make sure that that becomes positive with those absolute values. Subtract 1 from it, square it, and then divide by that denominator. I'm going to go ahead and round 3 decimal places. So we get 38.402. So that is going to be our lower bound. Again, that test statistic is that starting value, and then going to the right on a chi-square distribution would give us that p-value. So in order to get our p-value, we are going to use chi-squared CDF, where again it's going to be lower bound, upper bound, and then 1, since that's our degrees of freedom. So lower bound is our test statistic. Upper bound is 1E99. And then the last value that you have is 1, which is your degrees of freedom. On your graphing calculator, you're going to go to second, vars, and look for chi-squared CDF. For me, it's number 8, so chi-squared CDF. Then we're going to enter in our lower bound, which is going to be the test statistic that we just came up with, and our upper bound, which is going to be 1E99, because that chi-squared distribution goes on forever to the right, and then our degrees of freedom, which for Macnamar's test is always going to be 1. So our lower bound for this problem is going to be 38.402, comma, our upper bound, which is going to be 1E99. And remember, E, to get that, you hit second, comma, and then comma, our degrees of freedom, which for this case is 1. Select enter, and we get a value. Notice that it is e to the negative 10, which means times 10 to the negative 10th power. And so rounding this 4 decimal places, it should round to 0.0000. From the calculator, we get a p-value equal to 4.217 times 10 to the negative 10th, which again rounds to 0.000, which is going to be less than alpha, and in this problem alpha was 0.05. So this means that we are going to reject H0, our null hypothesis. So in conclusion, we can say there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that there is a difference in opinion of taxes paid by high income and low income people.